For this lesson, we are going to walk through 4 different examples of growth and decay models, including Newton's law of cooling. For our first example, we're going to look at growth. The number of bacteria present in a culture at time t in hours grows based on this function. This function should look familiar to you. It's the same thing as continuous growth for interest. So based on this, we should be able to answer these questions. Number 1, let's determine the number of bacteria at t equals 0. In other words, at time 0, before we started to grow. Well, remember what these values represent. This 1,000 here represents our present value. So if it was an investment, we would have started with 1,000. We're talking about bacteria though, and so the number of bacteria at the start would then be 1,000. How about the growth rate? Well, remember that E is raised to the RT and R is the rate. So in this situation, our rate is 0.01, which translates to 1%. Let's go ahead and graph this in our calculator and sketch the graph. Here is the graph of our continuous growth of bacteria. And we assume that bacteria is constantly growing. It doesn't wait a day and then divide. It is constantly dividing and is constantly growing. So we have a continuous exponential growth curve here. Let's look at our next question. Our next question said, algebraically determine the population after 4 hours. Well, if we go back to our graph, let's look and see what it might be after 4 hours. So how can we find that? We would need to find 4 on the x-axis and determine where it intersects on the y-axis. Our x-axis is our independent variable in hours, that's our time, and the y-axis is the number of bacteria. One thing we can do is type x equals 4 in order to graph a vertical line, find that intersection point, and we can see that after 4 hours our bacteria has grown to 1040.8. But let's prove that algebraically. Here is our equation. We want to find the number of bacteria after 4 hours. So we've plugged a 4 in for t. Now what we need to do is we need to take E and we need to raise it to the 0.01 times 4 power. Once we do that, we can multiply this by 1,000 to find out our answer. And we get the same answer that we got graphically, so we know we've done it right, 1040.81. Let's look at the last question here. When will the number of bacteria double? So we want to solve this algebraically and graphically. Let's go ahead and look at it graphically first. We started with 1,000 right here. And we want to know how long it takes for a bacteria to double, to reach 2,000. Well, there's a couple of things we could do. We could just trace the graph in our calculator until I get to 2,000, but you can see this is very difficult to get an exact value. It's approximately 69.4, but I'm unable to get to 2,000. There's some other strategies we can do in our calculator to get the exact value. What I can do is I can graph a horizontal line this time at 2,000, y equals 2,000, and then I can find the intersection point and that gives me an exact value. So I know that my bacteria will double after 69.3 hours. Let's go ahead and prove that algebraically. Here's my equation. So I'm looking for when the bacteria will be 2,000 if I started with 1,000. Go ahead and pause the video and see if you can get the same amount of time that we got graphically. See if you can remember how to solve this. Okay, in order to solve this, we know that we need to solve for t. We need to isolate t. So the first thing we need to do is move the 1,000 to the other side by dividing both sides by 1,000. On the left side then we'll have 2 equals E raised to the 0.01 t. What can we do from here? Hopefully you remember that if you have a variable in your exponent, in order to bring it down, we need to change this to be a logarithm. So the best thing to do from here is to go ahead and take the natural log, and I'm saying natural log because we have e here. And if you remember what a natural log is, natural log and e will have a special relationship together. So let's go ahead and do that. Now that I've taken the natural log, I need to simplify. Well, the first thing is I know that this power here can come down in front as a factor. But what about natural log e? What do you remember about that? Well, natural log is the same thing as log base e, and then we have an e. So what this is saying is, what power can I raise e to get e? And we know that power has to be 1. So in other words, natural log e is the same thing as 1. Let's go ahead and write out what we have then. On the right side, 0.01t times 1 will still be 0.01t. Natural log of e is just 1. Now to solve, all we need to do is divide both sides by 0.01. These cancel, and we can put this in our calculator. In my calculator, I have to do 2 natural log divided by 0.01. You might be able to just do natural log and then 2. And I get 69.31. And if you remember, graphically, we had 69.3. So we know we've done our math correctly. Let's now look at a decay model. Notice in this model, the only real difference between decay and growth is that we have a negative growth or decay rate. So, number 1, what is the decay rate? We know it's decay because of the negative, and the rate is 0.087, which is the same thing as 8.7%. Now let's graph this in our calculator and sketch the graph, and then we'll determine how much is left after 9 days. Here's what it looks like graphically, and you can see that it's clearly a decay model. In order to figure out how much is left after 9 days, I could have just traced this graph with my calculator, but you can see that it's hard to get an exact value. So what we've done instead is I've graphed the vertical line x equals 9 and found the point of intersection. So I know that 45.7 is going to be my solution. Graphically, I can show, or I should say algebraically, I can prove what I just did graphically by plugging in 9 in for my t, putting this in my calculator and solving, and I end up with 45.7. How about number 4? What is the half-life? Think for a minute about how you might solve this, and then come back. In order to solve this, you have to understand that the half-life means how long it will take for your initial sample to be cut in half. In other words, for the future value to only be 50 milligrams. In this case, here's our equation. We started with initial or present value amount of 100. We still have the same decay rate, and we need to solve for time. So this is just like the previous problem in that we have to solve for t. First step would then be to divide both sides by 100, and we would end up with 1/2 on the left side, which represents our half-life. And now we can take the natural log of both sides in order to solve for t. Remember, taking the natural log of the right side, we'll just leave the negative 0.087t. And then in order to finally solve for t, we can divide both sides by the negative 0.087. These cancel, and we can put this in our calculator to determine that the half-life is 7.967 days. So every approximately 8 days, the amount of the substance decays by 1/2. Let's examine one more decay model. For this model, go ahead and pause your video, see if you can solve this problem, and then come back and we'll do it together step by step. Our first step will always try to be to build our model. So our future value will always be equal to our initial amount or present value times e raised to the decay rate times time. In order to actually solve this problem, we need to know what that rate is. That'll be our step 2. This is an important step. Where did I get the 5 from? Well, remember that the half-life of radium is 1690 years, which I plugged in for time. We know that after 1,690 years, our substance has decayed by half, so we would only have 5 grams left. Now we can go ahead and solve for k in this problem. First, I divided both sides by 10 to get 1/2 here. Then I took the natural log of both sides, which left me with negative 1690k here. The final step then to figuring out our decay rate is to divide both sides by negative 1690 and then put this in our calculator. Now I have my missing decay rate. Notice that I carried out the values beyond the decimal point pretty far, and that's because the farther I carry it out, the more precise I will be in my final answer. To determine how much will be present in 50 years, I now can replace the negative k with the negative 0.00041. Then I can plug in 50 for my time. This can all be put into the calculator and solved in order to determine that the amount that will be present is 9.797 grams from my calculator. So remember, the important thing about these problems is that you're not always given this constant, and you need to find it in order to solve the problems that they give you. Let's look at our last problem, which is Newton's rate of cooling. In this problem here, this is Newton's law of cooling. This is the equation that is used. There's a lot of t's, but notice the subscripts. In this first part here, this is like our future value, where t is the time that has gone by to give us this temperature. T sub s is the surrounding or ambient temperature. T sub o is the initial temperature. In other words, if we take a pot roast out of the oven, it will have an initial temperature of maybe 150 degrees before it starts cooling. And then we have T sub s again, times E, raised to the negative k. Right now your brain should be thinking, well, that's a decay rate, which it would be if we're looking at how things cool, times time. And looking at this initial problem, it says a thermometer reading 72 degrees is placed in a refrigerator where the temperature is a constant 38 degrees. If the thermometer reads 60 degrees after 2 minutes, what will it read after 7 minutes? You should be thinking to yourself, nowhere in here does it give me the cooling rate or the cooling decay rate. So I'm going to have to find that. You can see that in this problem, they gave us S, which is the ambient temperature. They gave us the initial temperature of the body, 72 degrees. We know this, so really the only unknown we have is the K. Let's go ahead and use the 60 degrees in the 2 minutes in order to help us solve for K. In this case, we've plugged in our 60 for our future value. Our thermometer reads 60 degrees after 2 minutes, which I plugged in for T. Now let's go ahead and simplify. First thing is to subtract the 38 from the 60 to get 22. Then I'll divide both sides by 34 to get 0.647 on the left. And that'll leave me with e to the negative 2k on the right. Now I'm ready to take the natural log of both sides. And we know that taking the natural log of the right side will just leave us with the negative 2k. Finally, dividing both sides by negative 2, I'm going to figure out what my constant is. And when I put this in my calculator, I get negative 0.218. From here, we are ready to actually solve this problem to determine what it will read after 7 minutes. It's just a question of taking our constant rate, plugging it in here, and then taking 7 minutes and plugging it in for t. Putting this into my calculator, I end up with 45.39 degrees Fahrenheit. That is what my thermometer will read in the refrigerator after 7 minutes. Now let's look at 2. How long will it take before the thermometer reads 39 degrees? Setting up the equation, consider 39 degrees is our future amount, so it goes out here. The rest of the equation stays the same. Now I'll just need to simplify in order to solve for t. First, I'll subtract 38 from 39 to get 1, and then divide both sides by 34. At this point, hopefully now you realized that what we need to do is take the natural log of both sides in order to bring down our exponent so that we can solve for t. Finally, if we divide both sides by negative 2.218, we can then see that the time it will take to read 39 degrees will be 16.18 minutes. Now let's graph the relationship between time and temperature in our calculator and sketch our graph. Here's a picture of our graph. Notice what's going on here with the graph. We are decaying, we are cooling rapidly, and then what's happening? Let's look at the last question. It says, trace for large values of time. What do you notice about y? Well, as we move out over time, look what happens to our y value. It starts to approach some sort of constant amount. And if you'll notice, 38.3, 38.2, I can continue on, 38. It really just approaches 38. If you'll notice in our equation, let's go back, 38 is our constant temperature of the refrigerator. So at some point, what we're cooling will not go below 38. So y is approaching 38 is what's happening. And that concludes our models for today on growth and decay, as well as on Newton's law of cooling. So hopefully you're able to build the models and solve for whichever variables you need to in order to complete the problem.